Okay, this is your solid and hazardous waste video. It corresponds with your chapter 21 PDF reading. I'm just calling this waste disposal. We're focusing on two major things here: municipal solid waste and hazardous waste. Hazardous waste, because of its hazard, has to be treated a little bit differently. When we say municipal solid waste, excuse me, we really mean the garbage that you're used to, the trash that's generated by your municipalities, by your communities. So after I do a brief introduction, we'll talk about those two things. Something I need to point out to you is that there's a mistake in your book. Your reading is incorrect in the sense that it says a solid waste has to be a solid, and that's not the case. If you look at the RCRA definition, I've given you a web page address here, and you can look at that hyperlink. But RCRA stands for Resource Conservation Recovery Act. You don't need to know that, but it's basically the way EPA defines a solid waste. It can be a solid, a liquid, or a gas. It's just an odd use of a term. For lack of better words, they call it solid waste, but it does not have to be a solid. And you can look at that link and see that. This is basically taken from that link to make sure you realize that, that does not have to be a solid. So we look at sources of solid waste, and this is specifically the U.S. You'll notice that mining and oil and gas production is number one. You generate a lot of waste rock and earthen material, and that's why you're getting such a large amount there. And agricultural is the next biggest one, followed by industry. You can see the amount of waste that we generate as far as trash is actually fairly small compared to the total waste that we generate, but still important. We would look at mining and oil and gas production. These produce huge amounts of waste. So we think about municipal solid waste. That's really, like I said, the garbage that you're familiar with. Greater than 50% of this goes into landfills. The rest is either going to be incinerated, which I think is like 15% in this country, composted and recycled is the rest of it. It's a huge amount of material that we're not actually, handling in an appropriate way, because most of this stuff can be recycled and composted. When you look at it, I've got two numbers for you here. The blue ones are 2012, and the original figure, without the blue squares, is 1997. You see glass has been pretty steady, 5-6%. Metals, 8-9%. Plastics are up from 9 to 13%. Wood is fairly steady at 5-6%. Food is up to 15%. Yard trimming's up slightly. Paper and paperboard is actually down, because that's the one thing we actually, kind of recycle somewhat successfully. But you look at the amount of paperboard that still dominates the landfill. Okay, this is the composition of municipal solid waste that winds up basically in a landfill. So it still dominates the waste, and pretty much all of that can be recycled. There is a limit to the number of times you can recycle paper, but you can always turn it to other types of material, like packaging material and things like that. And then ultimately it breaks down so much of the fibers that a lot of it to some extent can just be composted and used as a filler in various places. All your glass and metals are recyclable. Most plastics are recyclable. Some require a little bit different, more advanced technology. Wood, food, you can see most of this stuff is recyclable, so we could really cut down tremendously the amount of stuff that goes into our landfills. So with a landfill, they're either going to be literally dug out areas of land or raised up above. So if you look at the one in Murfreesboro, it's a Rutherford County landfill, but it's in Murfreesboro, and it's right there past the VA hospital on your right as you head past up towards Walter Hill. It's probably the tallest spot in Murfreesboro. It's pretty large now, and that's because it's mainly above ground, because here in Murfreesboro, this area, Middle Tennessee in general, you don't have a lot of deep soils. You hit a lot of rock early. If you have an area that doesn't have much rock and you have deep soils, you can dig out that soil and put it more in the ground. But each day's waste is covered with soil. Hazardous materials should not be going into a landfill, so they should not be going into your trash. Here locally, we do have hazardous waste pickups, so you're going to want to utilize those so these things don't wind up in landfills, because the landfills do leach. We'll learn about that here in a second. They tend to be anaerobic because they're just big mounds of trash, basically, and there's not going to be a lot of oxygen in the middle of that. We learned about what that means, anaerobic, aerobic. So that means it's going to be slow to degrade. Aerobic things degrade faster and they degrade more completely. Anaerobic goes really slow. If you remember how petroleum is formed way back in the before spring break, is that we have insufficient oxygen, so the bacteria can't break it all the way down. So you wind up with material left over, organic material left over. If it was aerobic, it probably would have been broken down mostly to CO2 and water and then all of the metal minerals left over. But now you're left with bulk material. And in a landfill, there's documentation of people pulling out newspapers from the center of the landfill that are 50, 60, 70 years old, things like that. Things just don't break down. So when things do go anaerobic, I mentioned this before when we talked about climate change, this is a source of methane, and methane's a big heat-trapping gas. We mentioned swamps, wetlands, cows belching methane. Well, landfills produce methane, and most landfill operations do not collect the methane. However, you can collect it. A lot of them just burn it off, and sometimes at night you'll see actually, flames being torched off at landfills. It's just them burning off the methane, and that's actually a waste because it's a fuel. So it's kind of silly. We should be capturing this and using it. Some landfills will capture it and use it to run part of their operation. As of 1983, so it's been a while now, liners, leachate collection, and groundwater monitoring are all required for what we call these sanitary landfills. So this is an example of a modern sanitary landfill. You have to realize in the old days they used to be just big piles of trash. Now they're not. A lot of engineering goes into this, as you can see. You've got liners, you've got leachate pipes to collect the leachate, and then we monitor the groundwater with these wells over here and testing it. And then we can pull up this leachate and it can be treated. Here's where you can actually capture methane, store it, and use it to generate electricity. So this becomes very useful. You notice the top covered with the day's soil. We also put clay liners in there as we stop adding more to it. Eventually, a landfill will be capped with a clay liner. Clay is just, type of soil that's very impervious. So you don't want a bunch of water getting into your landfill and having such leach out. So down here, you typically also have clay, as you can see, and then you got plastic liners, and then you've got your subsoil there. So that's a blow up of the bottom of the landfill, and this is a blow up of the top of the landfill. So that's in general, and this refers to a figure in your book that's very similar. So if you don't want to landfill it, you've got to do some other things. And obviously the ideal thing to do would be reduce, recycle, and reuse, the 3 R's. Reduce the amount that you generate. You go to the grocery store, now you buy potatoes, and they're packaged in styrofoam with plastic wrap rather than just being loose. This adds to the waste that we generate. So if you can buy bulk loose stuff, it's better. Less packaging. But you can also reuse stuff. You can find different uses for it around your house and keep it for a while and not just throw it in the trash, get multiple uses out of it. And then, of course, you can recycle. And then we can recover those materials and use them to make similar materials or something completely different. Composting, of course, is a great option for any food-type material and even things like newspaper and stuff like that breaks down. I have a compost pile in my yard. We just continually add to it, and then you can add it to your garden, your soil, and use it as a good soil amendment, and it breaks down tremendously. The volume of waste I put in there compared to what I get out of it is tremendous. I mean, you just have the bacteria just completely breaking this stuff down, and you're left with the rich soil. So it's very useful, eggshells, and all this types of stuff. But if you're not going to reduce, recycle, reuse, and you don't want to landfill, another option is to incinerate it. And in the U.S., we only incinerate about 15% of all of our waste. Advantage of this is that it reduces your waste by 85%. So if you start out with a kilogram of waste, you're going to wind up with 0.15 kilograms when you're left over with. So 85% of that will be broken down. You kill any pathogens that are there. There's no water pollution associated with it. You can get energy out of it. Now you can use this food and feces and manure and stuff like this as a fuel. So effectively you can use it to power a building, electricity. And metals can be recovered. In fact, when I first moved to Tennessee in Nashville, there was a waste to energy plant. That's what WTE stands for, waste to energy. And used to power a good number of buildings down in Nashville. Unfortunately, it caught fire and burnt down. That was years ago, and that's no longer there. But there are some disadvantages, and there are serious concerns. The ash can be hazardous waste, depending on what's going in there. It's going to be important that you recover metals and things like that. But this is where dioxins can form. We mentioned that phrase before. It's in our kind of slides that have like the persistent organic pollutants listed and stuff like that. Dioxins, I said, were not produced by humans. They're just formed in high temperature combustion reactions with organic materials and chlorine. Chlorine has to be present because all your dioxins are chlorinated compounds. They're those chlorinated organics that are recalcitrant that we talked about, similar to DDT. Of course, DDT is a pesticide and insecticide. And air pollution is a big concern. So burning stuff, there's this whole phrase, yeah, I'm okay with incineration, just not in my backyard, right? Because nobody wants to be breathing it. Um, so even when run correctly, there is going to be some air pollution issues, but there are ways to create elaborate systems that can do after burning and reburning. So those are your options really for dealing with municipal solid waste or just your basic garbage. Now we get into hazardous waste. And these pose a much more substantial risk to humans. They're mostly produced by industry. Obviously, these are not things we're producing. We might be purchasing in them and then have them in our possession. The three main culprits here are going to be the chemical industry, the petroleum industry, and metals-related industries. And you have three options. The best option, of course, is just produce less. But if you can't do that, or at least with some of it, you want to convert it to less hazardous materials. So there are treatments we can do to make it less hazardous. If not, then you have to long-term storage it. So you can refer to a figure there. There's a figure in your book that shows this. Here's kind of the levels of desirability. The first one is produce less. And this is where green chemistry comes in. And green chemistry is really just chemistry applied to the processing of things that is sustainable, benign. We don't produce a lot of hazardous chemicals. We don't waste things. We do things in a different fashion than standard processing. So it's to replace, say, a material that winds up producing a waste with something that doesn't produce a waste, or replace something that's toxic with something that's non-toxic. And of course, less desirable will then be, to convert it when you're done. There's lots of things here. Your book goes into a few that I'm not holding you responsible for, but you can incinerate it, you can land treat it, thermally treat it, chemically, physically, biologically treat it. There's different options, and if you can't treat it, then you've got to store it. And this is the worst choice, of course. Underground injection I'll talk about. I'll talk about the landfills. They're slightly different, but you can use surface impoundments. I'll show you a figure of that. Then there's just waste piles. You can put into salt formations, which are basically abandoned areas where we've mined salt. So there's different options there. So here's long-term storage option. This is a landfill. This is called a secure landfill. And the big difference here between a regular landfill and a secure landfill is the reactive waste are placed in separate drums. Okay, you still got your groundwater monitoring. You usually have a, double leachate collection system. So double lined up in leachate collection. But you still have the monitoring wells. You still have the impervious caps. So that's all very similar. The main difference is that collect the storage is in individual drums. And you do have additional leachate collection usually. But another option is deep well injection. A lot of people are not even aware that we do this. And not only do we do it with 60% of all of our liquid hazardous waste. Not 60% of our hazardous waste, but 60% of our liquid hazardous waste. Most of our hazardous waste tends to be more liquid. There's a decent amount of solid too, and some gases too. So the idea here is that we pump it deep, deep underground. In this case, this one's showing you about 1,000 meters. We go even deeper than this. And the idea is there's no water down there that we're using. Here's your water table up here. It's separated by many layers. This is impermeable. And here's this permeable, disposable area. So it's going to be like a porous type rock, similar to what an aquifer runs through. And it's going to be surrounded by impermeable layers. So the idea is it can't get out. However, the big problem with that is that these layers, which are going to go on for miles, of course, can often have cracks in them. Okay? And then if this waste is pumped in here, I'm going to pump in some waste here, and it starts to fill in, it hits this crack, and this crack now extends through the earth into maybe another layer that's going to lead to water. This waste can now travel through that crack into possibly your water table. So there is concerns with that, how deep it is and how close it is to waters. And there's all different sorts of classifications of wells and different types that can be utilized. There are shallow ones also. There's like 6 different classification of wells that we're not going to go into. Another option is just storing it in a surface impoundment above ground. So in this case, again, you've got an impervious layer when you've got plastic liners, and the idea is to minimize that leaching. But all these plastic liners, they wind up ripping and tearing, just like in landfills. EPA makes comments like, statements like, every landfill leaks. I mean, basically, the liners just eventually tear. There's animals that rip through them, weather, deterioration from chemical degradation, all that kind of stuff. But this is what these things can look like. They're not exactly pleasant to see. They're eyesores. This is just a crude way of storing waste above ground. Now, the last thing I want to mention, and you're not really responsible for this, but it's important that you're aware of it, I feel like. So it's radioactive waste. And radioactive waste is treated completely differently. And there's a couple slides, additional slides in your slides posted as opposed to this video. But the idea we had come up with all our radioactive waste, which is scattered all over the country as a result from the nuclear era of developing nuclear energy and nuclear bombs from the Cold War and all of this. We've got lots of waste scattered everywhere, and it's not protected very well. So the idea we came up with is to come up with this huge repository to store it all. This was in Nevada, and this shows you the entryway, and this went into major production, and we spent billions of dollars developing this to store all of our waste. But then eventually people in the home state of Nevada got, for legitimate reasons, got cold feet, if you will. You can see we produced this thing. This is a interior shot of this. There's a lot of technology that went into this and a big cost. The idea was to store this stuff underground. Some geologists started questioning whether this was a sound way of doing it, because a lot of this radioactive waste, as we learned, is radioactive for thousands of years. So if you have an earthquake, seismic activity, it can cause breaches in this thing. It can cause, collapsing of part of the facility and leading to drums that are stored there being compromised and leaking. And if this gets into your groundwater, small amount of radioactivity into your groundwater basically renders that a useless drinking water source for thousands of years. So that's one reason it was abandoned. So we're back to square one, basically. I'm not sure what they're going to do with this thing. But that concludes the video for now, and make sure that you look at the material and read your chapter.